Welcome to Talk Tensors.
It is good to be back.
Today we are opening up a topic that is, I think, arguably one of the most paradoxical corners of the current artificial intelligence landscape. It's a subject that really forces us to look past the dazzling surface of what we see on our screens and ask a very, very fundamental question about what these machines actually understand.
Precisely. We are in this strange moment where the output of AI, specifically video AI, has become incredibly convincing. I mean, just astonishingly good.
Right.
We have models like Sora and its successors generating scenes that look like they're from high-budget cinema. The lighting is perfect, the textures are hyper-realistic, the camera movements, they're impossibly smooth.
It looks real. To the naked eye, it's often indistinguishable from reality.
It is.
Yeah.
But, and this is the big but, there is a massive discrepancy, a sort of hidden chasm between the ability to generate those pixels and the ability to actually understand the sequence of events they represent.
It's the difference between a parrot reciting Shakespeare and a scholar analyzing it. The parrot sounds perfect, the phonetics are flawless, but does it know why Hamlet is upset? Or is it just a sequence of sounds it's been trained to mimic?
That is a fair analogy, but I'd argue that in this case, it's even more fundamental. It's not just about emotional nuance or literary context. It's about the very physics of time itself.
And that's the central theme for this deep dive, isn't it? What researchers are calling the time blindness paradox.
That's the one, time blindness.
It sounds like a medical condition or maybe a sci-fi trope, but we're talking about state-of-the-art neural networks here.
We are. Let's call it the dirty secret of computer vision right now, is that many of our best models, the ones currently valued at billions and billions of dollars, are essentially time blind.
Okay, so unpack that. What does that mean in practice?
It means they process video not as a flowing river of cause and effect, but as a stack of unrelated photographs. They see the what and the where, but they are failing, and I mean spectacularly failing, at the when.
Which is wild when you think about it, because we are starting to entrust these models with things like autonomous driving, security monitoring, robotic.
All things that depend on time.
Exactly. If a robot is time blind, that seems, well, more than problematic. If it doesn't know that the ball rolling into the street now means a child might follow in the next 2 seconds, we have a massive safety issue.
To say the least. It's the difference between seeing a static image of a car crash and watching the events leading up to it to understand who is at fault. One is a snapshot, the other is a narrative.
A narrative built on time.
Exactly.
Yeah.
So our mission for this deep dive is to unpack this shift. We are moving from the era of image pre-training, where we just teach models to look at photos, to true temporal reasoning.
And we're going to look at this emerging thinking with video paradigm, right? Specifically how generation models, like the Stora 2 paper we've got, are now being used for reasoning.
Yes, that's a huge piece of the puzzle. But we also have a heavy stack of other papers to get through. We're going to break down the new AIM architecture.
Which is all about efficiency, adapting the brains we already have to see time.
Correct. Then we're going to look at Meta's VJP2, which is this incredibly ambitious attempt to build a world model for physical intelligence, essentially teaching AI the intuitive physics of the world.
Like gravity, momentum, that kind of thing.
All of it. And of course, we have to talk about the benchmarks that kind of blew this whole problem wide open in the first place. Spooky bench and TV bench.
Oh, yes, the smoking gun.
Those benchmarks are the smoking gun. They really peel back the layers of hype to show us what's actually broken under the hood.
So let's start exactly there. Let's unpack the problem. Why do we say these models are lost in time? If I show an AI a video of a dog catching a frisbee and I ask it what is happening, it can tell me a dog is catching a frisbee. It gets the caption right, so where's the failure?
The failure lies in how it arrived at that conclusion. You see, current video vision language models, or video VLMs, have a very, very strong spatial bias.
Meaning they're good at recognizing things in a single picture.
Incredibly good. They see a dog, they see a frisbee, they see a park, they see the dog is in midair. They take all those nouns and those static states, they put them together, and they guess the verb based on statistical likelihood.
So they are guessing based on the scene context, not the motion itself.
Yes.
It sees dog plus frisbee plus park, and the most probable verb in its database is catching. It doesn't actually see the catch happen over a sequence of frames.
You've nailed it. This is what researchers are now calling the coherence gap. The model sees a person and a swimming pool and says swimming. but it didn't actually watch the strokes. It didn't verify the motion of the arms, the splashing of the water.
It just recognized the static element.
It's like a detective walking into a crime scene, seeing a gun on the floor and a body, and immediately declaring shooting without actually checking the ballistics or the timeline or any of the evidence.
It's a shortcut, a statistical inference. It's
Yeah.
cheating. It's like a student who didn't read the book but memorized the SparkNotes summaries of the characters and the plot points.
Effectively, yes. And this is where Spooky Bench comes in. This is a fascinating benchmark designed specifically to stop the models from cheating in this way.
I love the name, Spooky Bench. It implies something ghostly, something not quite there.
It is so appropriate because it deals with what you could call ghostly data. The researchers realized that to truly test time, they had to destroy space. They had to remove all the visual crutches the models were leaning on.
So what did they do?
They created video tasks where the individual frames effectively look like noise, like static, or abstract patterns.
Paint a picture for me here. If I pause the video and look at a single frame, what do I see?
You see nothing. Genuinely nothing meaningful. Maybe a random scatter of black and white dots or the screen of static like an old detuned television set. If you showed that one frame to a human or to an AI and asked, what is this? The only correct answer would be noise.
Okay, so the static image itself contains zero semantic information. There's no dog, no frisbee.
Correct. The only information exists in the change over time. The motion itself creates the signal. Imagine the static dots are moving in a way that over a second they trace the shape of the square. But you can only see that square when the video is playing. The moment you pause it, the shape dissolves back into the noise.
So you strip away every object, every texture, every spatial cue. All that's left is pure time. It's like those old magic eye posters, but instead of crossing your eyes to see the hidden image, you have to press play.
That is a perfect way to visualize it.
Yeah.
It isolates the temporal dimension completely, and the results from this benchmark, they were shocking.
Let's hear it.
When human participants took these tests, identifying patterns that only exist in motion, they achieved about 98% accuracy.
Which makes sense. It's natural for us.
Completely natural. Our brains are hardwired for temporal processing. We evolved to track movement for survival. A predator in the tall grass might be perfectly camouflaged and invisible when it's still, but the moment it moves, our visual system locks onto it instantly.
Okay, so humans at 98%. What about the AI, the heavy hitters?
The state-of-the-art video LLMs. So we're talking about models like GPT-4o, Gemini 1.5 Pro, Qwen 2 VL, the biggest names, the models that power the services we use every day.
The ones valued at billions of dollars.
Those ones. They scored near 0%.
Zero. Not like 10% or 5%, just zero.
Near zero. Random chance, or in some cases worse. They simply could not see the pattern because they were looking for objects in the frames and there were no objects to find. They were completely, utterly blind to the temporal dimension. Wow. They were scrutinizing the static noise, looking for a dog that wasn't there, and completely missing the motion that was screaming right in front of them.
That is a staggering gap. 98% for us, 0% for the smartest AI on the market. It really, really drives home that point about the stack of photos. If you look at a stack of noisy photos, you still just see noise. You have to watch the movie to see the pattern.
And it gets worse. TV Bench, another one of these temporal benchmarks, tried a very simple test, shuffling the video frames.
Oh, I see where this is going.
If you take a video of someone making a sandwich, slice bread, get jam, spread jam, put slices together, and you shuffle the frames so the order is random, a human would immediately say, wait, this makes no sense. The bread is being toasted before it's put in the toaster. The jam is being spread before the jar is opened.
Right. Cause and effect are broken. The entropy is all wrong. The arrow of time is snapping back and forth. It's a mess.
But for many of these top models, shuffling the frames resulted in no significant drop in performance.
That's damning. That's the proof right there.
It is.
That proves they weren't paying attention to the order in the first place.
If the order of events doesn't matter to your answer, you aren't understanding the video. You're just summarizing the ingredients. I see bread, I see jam, I see a knife. Must be a sandwich.
Precisely. If I hand you a shuffled deck of flashcards telling a story, and you tell me the story perfectly, it means you either already knew the story, or you're just guessing based on the words on the cards, not reading the actual sequence.
And this has real-world consequences, beyond just getting video captions wrong. Absolutely. The papers highlight some very specific and worrying failures. For example, models consistently struggle to distinguish between pulling something from left to right versus pulling something from right to left.
Because in a static frame, or an average of frames, pulling looks the same regardless of direction. You need the vector of time to know the direction. A photo of a car on a highway doesn't tell you if it's going north or south.
Exactly. And here's a really subtle one they found. Distinguishing between spilling something behind an object versus pretending to turn something upside down.
Oh, that's tricky. The visual elements are nearly identical: a cup, a hand, a rotational motion. But the physics, the actual liquid leaving the cup versus staying in, that happens over time and might even be occluded.
And that is where the time blindness hits hard. It's like trying to read a book by picking random words off the page, but ignoring the sentence structure. You might get the topic, "This is a book about whales," but you will completely miss the meaning, "The whale ate the captain."
Or the captain ate the whale, which is a very, very different story.
Exactly. The sequence is the story.
Okay, so we've established the problem is deep and fundamental. The current approach, basically taking a big image model and showing it a few video frames, is flawed, but we also know that training these massive video models from scratch is, well, prohibitively expensive.
That's the practical constraint. Video data is huge. You can't just feed petabytes of 4K video into a transformer without, melting a data center.
We can complain about time blindness all day, but if fixing it costs $1 trillion in compute, it's just not going to happen.
That is the engineering bottleneck. We need temporal understanding, but we cannot afford the computational cost of training these massive brains from the ground up on video. The compute tax on video is exponentially higher than on text or images precisely because of that third dimension time.
Which brings us neatly to the second part of our stack here, the AIM solution. Adapting image models. Now, this sounds like a compromise, but the paper suggests it's actually a breakthrough in efficiency. It sounds like they're trying to recycle the brains we already have.
It's a very clever architectural hack. The core idea of AIM is to say, look, we have these massive, brilliant image models like VIT, the Vision Transformer, or SWIM Transformer. They've been trained on billions of images. They already know what a car looks like. They know what a dog looks like. They have immense spatial intelligence.
Right. That knowledge is valuable.
Extremely valuable. So let's not throw that away. Let's not start from scratch.
So we keep the frozen brain. We don't lobotomize the model to teach it something new.
We keep the backbone frozen. We don't touch those pre-trained weights. Instead, we use adapters. These are very small, lightweight modules that we sort of attach to the model, like adding a sidecar to a motorcycle. Or, a better analogy might be putting a pair of time glasses on a static observer who's brilliant at seeing pictures.
I like that. The observer is already an expert on photos, and you're just giving them a new tool to perceive time. So these adapters handle the time part.
Exactly. They introduce a few types of adaptation, but the temporal adaptation, they call it TMSA, is the really ingenious part. They reuse the same self-attention layer that was pre-trained for looking at images.
Wait, okay, you have to unpack that for me. How do you use an image attention layer, which is designed to look at patches of pixels in a square to understand time? An image doesn't have time.
It all comes down to how you shape the data before you feed it in. Usually, an image model like a VIT breaks an image into patches, little 16 by 16 pixel squares, top left, bottom right, and so on. It then calculates attention between these spatial patches to understand the whole picture.
Okay, that makes sense. It sees how the ear patch relates to the nose patch to recognize a face.
Right. For the temporal adapter, they take the video input and they essentially reshape it. Instead of feeding it patches from across space within one frame, they feed it a sequence of corresponding patches across multiple frames.
So they trick the image attention layer into looking at frame 1, frame 2, frame 3 as if they were just different patches it needs to analyze.
In essence, yes. They reshape the input tensor from batch height width to something that represents batch time features. The underlying mathematics of the attention mechanism doesn't actually care if it's attending to pixels or to time steps. It's just calculating relationships. It's a function that asks, how much does A relate to B? By feeding it time data, that frozen pre-trained image layer learns to calculate the relationships between frames. It starts to ask, how does the state of this patch in frame 1 relate to its state in frame 2?
That is wildly efficient. You're not training a whole new brain. You're just presenting the data differently to the old, very smart brain. You're teaching an old dog a new trick just by changing the command.
And because they're only training these tiny adapter layers, the number of tunable parameters drops to the floor. We're comparing AIM, which has about 11 million tunable parameters, against something like Timesformer or Video Swin, which requires full fine-tuning of the entire 121 million parameter model.
That's a 10x reduction. That's massive for deployment costs, for energy consumption, for everything. That means you can actually run these models on smaller, more accessible hardware.
And the performance is not just comparable. In some cases, it's better. Specifically, AIM shines when training data is scarce. They show that with only 1% of the available training data, AIM significantly outperforms the fully fine-tuned models.
Okay, why is that? That seems counterintuitive. You'd think the model trained from scratch on video would be better.
It's because the fully fine-tuned models can often destroy their pre-trained knowledge while trying to learn the new task of video. It's a classic machine learning problem known as catastrophic forgetting.
Ah, right. They forget what a dog looks like while they're trying to learn how a dog moves.
You got it. The new learning overwrites the old valuable knowledge, whereas AIM keeps that solid foundation, the frozen backbone, untouched. The model never forgets what a dog is. It just adds a very light, efficient time layer on top.
It preserves the spatial smarts while grafting on the temporal smarts. It's the best of both worlds, at least for recognition tasks.
Exactly. So AIM gives us a practical, efficient way to build video models that don't bankrupt us. But it's still fundamentally a recognition tool. It labels things. It describes actions.
Right. AIM helps us solve the what is happening question efficiently. But let's zoom out. Recognizing that a man is running is one thing. Reasoning about why he is running or what will happen next because he's running towards a cliff, that's a whole other level.
And that brings us to the thinking with video paradigm.
This feels like a major conceptual shift.
It is. For the last few years, we have been obsessed with thinking with text. That's your standard large language model, your GPT, using chain of thought. We ask it to think step by step in words.
Then we had thinking with images where models could look at a picture and reason about it.
Right. But both of those are static modalities. Text is symbolic, images are snapshots in time. Neither of them truly captures dynamic processes, physics, or continuous change.
They're nouns, not verbs.
A great way to put it. The Thinking with Video paper proposes using video generation models. Specifically, they use a model they call Sora 2. Not just to make pretty clips for social media, but to reason.
This sounds like using an internal simulator.
It is effectively mental simulation. Think about how you solve a physical problem. If I ask an AI, if I drop this glass from my hand onto a concrete floor, what happens? A text-based model looks up the statistical probability of the words glass and breaks appearing together. It's retrieving a fact from its vast library of training data.
It's basically reciting a Wikipedia entry about the fragility of glass. It knows the answer, but it doesn't understand the process.
Correct. But a video thinking model would approach this differently. It would actually generate a short internal video, a mental movie of the glass falling, the acceleration due to gravity, the impact with the floor, the shattering, and the shard scattering.
And then it looks at its own generated video to answer the question.
Exactly. It uses its generative capacity to simulate the future. It thinks by watching its own imagination.
That feels so much closer to how humans think. If I ask you if a big couch will fit through a narrow doorway, you don't do trigonometry in your head.
Not at all.
You visualize it. You mentally simulate rotating it, tilting it, sliding it through. You run a little movie in your mind's eye to see if it works.
That's precisely the idea. The paper calls this a unified temporal framework. They tested this version of Sora on it, and the results are pretty impressive. It achieved 92% accuracy on the math benchmark and over 75% on multidiscipline tasks, the MMMU benchmark.
Wait, hold on a second. 92% on math. Why on earth does generating video help with math problems? Math is abstract. It's numbers and symbols. It's not about glass breaking or couches rotating.
That is the most surprising part of the paper, and it's a fantastic question. It seems that the ability to visualize a step-by-step process, even an abstract one, is deeply connected to the logical sequencing required for mathematics.
So it's about process, not pictures.
It's about maintaining coherence over a series of steps. Solving an algebraic equation is a temporal process. Step 1 leads to step 2, which leads to step 3. If you have a brain architecture that is fundamentally designed to track cause and effect over time, it turns out that brain is also very good at tracking logical steps in a proof or a calculation. It's using its video generation machinery to simulate the flow of logic.
That's fascinating. It suggests that reasoning and temporal simulation might be two sides of the same cognitive coin. If you can hold a timeline of events in your head, you can also hold a logical argument in your head.
Precisely. The structure is the same. But there is another twist in this section of the research called T3 textual temporal reasoning transfer. This one threw me for a loop.
Yeah, this was the part where I had to reread the paper a couple of times. It felt backwards.
It does. T3 challenges our assumptions again. We have been blaming the eyes of the AI and the vision encoder for being time blind. But T3 suggests the problem might actually be, or also be, in the brain, the LLM backbone that processes the information.
The language model itself doesn't understand the concept of time.
Think about it. LLMs are trained on static text from the internet. They read millions of books and websites. They see the sentence, "the vase broke," and the sentence, "he dropped the vase." They understand the semantic connection between drop and break, but they don't necessarily have a grounded, intuitive understanding of the temporal physics involved.
They don't know that dropping implies a duration of falling, that breaking is an instantaneous event that follows.
They view time as a literary device, a sequence of words, not as a physical dimension with rules.
So T3 is trying to fix the brain, not the eyes.
Exactly. T3 involves training the model on pure text temporal puzzles. No video at all.
Like those logic puzzles from school. John entered the room before Mary, but after Steve. Who entered first?
Exactly, those kinds of puzzles. Puzzles that force the model to construct a timeline and reason about it. Event A takes 5 minutes. Event B takes 10 minutes. If they start at the same time, which one ends last? Very simple, fundamental temporal logic.
Okay, so they train it on text puzzles. What happens?
And here is the kicker. Improving the model's ability to solve those text puzzles directly transferred to better video understanding.
Without showing it a single extra frame of video.
Without showing it any more video. Just by teaching the language part of the brain the abstract concepts of sequence, duration, and simultaneity via text, it became better at interpreting the visual signals of time that the video encoder was feeding it.
Wow. That implies that time blindness is partially a cognitive deficit, not just a perceptual one.
I think that's the right way to put it.
It's not just that the AI can't see the motion, it's that it doesn't have the mental framework to categorize before and after properly. It sees the pixels moving, but it doesn't have the file cabinet in its brain to store sequential data in the right order.
It is a bit of both. You need the eyes to see the motion, which Spooky Bench shows us the raw models are lacking.
Yeah.
But you also need the brain to process the sequence, which T3 addresses. You need both the sensor and the processor to be time aware.
Okay, so we have efficient eyes with AIM, and we have a simulating brain with SOAR 2. Now, I want to talk about Meta's contribution here, because they are taking a very different, almost philosophical approach with VJP2.
Yes, VJP2 is a beast. This is Jan LeCun's vision really coming to life. He's been talking about this joint embedding predictive architecture for years. And the key distinction here, the thing that sets it apart, is that it rejects the generative hype.
Wait, we just spent all this time praising SOAR 2 for being generative. Why is VJPA rejecting that approach?
Because VJPA focuses on representation prediction, not pixel prediction. Think about a video of a tree swaying in the wind. A generative model like Sora has to predict the color and position of every single leaf, every shadow, every blade of grass, every pixel in the next frame. It has to render the world in perfect detail.
Which is incredibly computationally expensive and, frankly, impossible to get 100% right because the world is chaotic.
And it's wasteful. Does it really matter to understanding the scene if leaf number 452 moves slightly left or slightly right? No. What matters is the underlying physics. The fact that the wind is blowing and the branches are swaying as a result.
Okay, so what does VJPA do instead?
VJP2 doesn't try to predict the pixels of the next frame. It predicts the abstract representation of the next frame.
It predicts the vibe of the physics, not the picture itself.
That's a great way to put it. It predicts the state of the world in an abstract mathematical space, an embedding space. It encodes the video into these dense vectors, just lists of numbers that represent the meaning of the scene, and then it guesses what those vectors will look like in the future. This forces the model to learn things like object permanence, gravity, and inertia, without getting bogged down and distracted by the noisy, irrelevant details of visual texture.
It doesn't care about the color of the paint on the wall. It cares that the wall is a solid object that things will bounce off of.
Exactly. It's focusing on the signal, not the noise.
So let's look under the hood a bit. How does it actually process the video? I saw the term tubelets in the paper.
Tubelets, it's a great word. In a standard image model, you chop an image into 2D squares, they call them patches. VJPA chops the video to 3D blocks, for example, 16 by 16 pixels across 2 frames of time. That little block of space-time is a tublet.
So the fundamental unit of data isn't a piece of a picture, it's a piece of an event. It has duration built into it.
Exactly. It treats time and space as a unified chunk from the very beginning. And knowing where that chunk fits in the bigger picture is critical. This is where they use something called 3D rotary position embeddings.
ROPP. We see that in large language models all the time. It's how the model knows that word 5 comes after word 4 in a sentence.
Yes, but this is 3D. It dynamically encodes the temporal position and the spatial position using rotational matrices. You can imagine a coordinate system that twists and turns as you move through time. It allows the model to have a very precise understanding that this tubelet is at coordinate xy and happened at time t. The paper says this was absolutely essential for stabilizing the training of these billion-parameter models. Without it, the model just gets lost in the sequence. It forgets if a tubelet happened 1 second ago or 10 seconds ago.
And the training process itself involves masking, right? Like a high-stakes game of peekaboo.
Hardcore peekaboo. They mask out huge chunks of the video, both in space and in time. They might block out the entire right side of the screen for 2 full seconds. The model's job is to guess the abstract representations of what's happening in that missing chunk.
So it's not just filling in a missing word in a sentence. It's filling in a missing event in a timeline.
And to do that successfully, it has to understand the physics of the world. If a ball rolls behind a box, which is the part of the screen that's been masked, and then emerges on the other side, the model has to mentally simulate that trajectory through the hidden zone to fill in the blanks correctly.
If it just guesses that the ball teleported or simply disappeared, the loss function punishes it heavily.
Right. It forces the model to learn object permanence. The ball didn't cease to exist, it just went through the mask zone, and it should continue on its path governed by momentum. If the model didn't understand physics, it would just guess random noise for the masked area. To get the prediction right, it must model the underlying reality.
And this isn't just for watching YouTube videos. The paper makes it clear that VJP2 is built for robots.
This is the planning aspect. This is where the rubber meets the road, so to speak. Because a robot that can watch a video is interesting, but a robot that can't act on what it sees is ultimately useless.
Yes. If you want a robot to clear a table, you can't just have it hallucinate a perfect video of a clean table. It needs to plan a sequence of physical actions.
And VJP2 does this using something called an energy function.
Energy in the physics sense, like joules.
In the mathematical optimization sense, though it correlates strongly to physics, think of energy as incompatibility or error. The robot has a goal image, a picture of the clean table. It has its current state, the messy table.
Okay.
It then imagines a sequence of possible actions. Grab cup, move arm left, rotate wrist. For each potential action, the VJP world model predicts the future state representation. Then it calculates the mathematical distance or energy between that predicted state and the goal state.
So it's constantly looking for the path of least resistance. The action that gets the predicted state closest to the goal state is the one with the lowest energy.
Correct. It uses a method called model predictive control, or MPC. It simulates thousands of possible action sequences, picks one with the lowest energy, and then, this is the crucial part, it executes only the first step of that plan.
And then it replans from the new state. That's receding horizon control. Why replan? Why not just execute the whole perfect sequence it found?
Because the real world is messy and unpredictable. Maybe the cup slips in its gripper. Maybe the table gets bumped. If you blindly stick to the plan you made 10 seconds ago, you might end up crushing the cup or knocking something else over. So you take one step, you look again, you replan based on the new reality, you take another step. This makes the system incredibly robust to the chaos of the real world.
That is a crucial distinction. A generative model dreams of a perfect world. A predictive world model navigates a messy one.
That's a bumper sticker right there. You've summed it up perfectly.
So tying this all together, we have Spooky Bench telling us the old models are fundamentally blind to time. We have AIM telling us we can adapt our old image models efficiently to see it. We have Thinking with Video telling us that simulation is a powerful new tool for reasoning. And we have VJP2 telling us that for real-world action, predicting abstract physics is far better than predicting pixels.
That is the landscape. We are moving from an era of hallucination to an era of simulation, from static recognition to dynamic understanding.
Which brings us to my favorite part of the show. We've looked at the facts, we've gone through the papers, we've examined the benchmarks. Now let's get a little speculative. It's time for novel notions.
And here's the disclaimer. These are hypothetical applications based on the tech we just discussed. We are extrapolating for entertainment and for thought experiments. Do not go out and build these without reading the safety manuals, please.
Absolutely. So notion number 1, the temporal lie detector.
Ooh, for deepfakes and forensics.
Exactly. We know from Spooky Bench that current AI models have this coherence gap. They don't get the fine-grained physics of time. Humans get it 98% of the time, but even we can be fooled by high-resolution deepfake videos. So could we build a security system, a kind of temporal CAPTCHA, that relies on subtle temporal causality that only reality adheres to?
So you're not looking at the pixels, you're looking at the physics, like asking a user to perform a motion that involves complex physics. Pour water from this cup to that cup in a specific way.
Or even just analyzing a passive video feed. A deepfake of a politician giving a speech might look perfect in every single frame. The skin texture is right, the voice is synced. But does the micro movement of their facial muscles match the physics of a real human face over time? Does the way their jowls subtly shake when they turn their head follow the laws of inertia?
Right. Skin has elasticity. It has mass and momentum. It's not just a texture map being warped.
If we run that video through a VJP2-style world model and the energy is high, meaning the predicted physics don't track with the model's understanding of reality, it flags it as a fake.
That is highly plausible. A physics consistency check for video forensics. If the shadow on the wall moves 2 milliseconds too fast for the light source in the room, the model flags it. It's using the AI's own weakness against itself. It forces the generator to not just paint a perfect picture, but to simulate biology and physics perfectly, which is an infinitely harder problem.
Notion number 2, generative simulation engineering.
This one sounds like it builds on the thinking with video paradigm.
Right. Currently, engineering is a slow, expensive process. You design something in CAD, you build a physical prototype, you test it, it breaks, you learn why, you repeat. It costs millions and takes years.
The R&D cycle.
What if, instead, an engineer describes a new jet engine in text and provides the material specifications? You feed that into a massive physics-compliant version of a SOAR 2 model. You then give it a prompt. Simulate this engine running at 5,000 RPM under these atmospheric conditions for 10,000 hours.
And because the model understands material fatigue, thermodynamics, and temporal causality, it generates a video of the engine eventually failing.
And it shows you exactly where and why it fails. Look, at hour 8,752, this specific turbine blade develops a microfracture due to harmonic resonance, and it leads to catastrophic failure. It reasons through simulation. You could perform a decade of R&D in 10 minutes.
It would be the ultimate digital twin, but one that can hallucinate physically accurate failures before you've even drawn a final blueprint.
Now, obviously, that would require a model with an incredibly precise internal physics engine, far better than what we have now. It would need to understand thermodynamics, fluid dynamics, friction coefficients, material science.
The whole 9 yards. But the trajectory is there. If thinking with video works for abstract math, which is a chain of logic, why wouldn't it eventually work for mechanics, which is a chain of causality?
It could revolutionize R&D. You could test 1 million different designs in the cloud before a single piece of metal is ever cut.
As long as you trust the model's physics engine. If it hallucinates incorrect physics, you could build a bridge that is certified by the AI and then it falls down in the real world. The stakes are high.
Yeah.
Very high. Okay, notion number 3, the T3 translator for animal communication.
Okay, take me there. This one feels like a big leap.
It is, but hear me out. We talked about T3 textual temporal reasoning transfer, transferring an understanding of time from text to video. What if we could reverse that process?
Go from video to text.
Animals don't write text, but many of them have incredibly complex communication systems that are based entirely on motion and time. Bees perform a waggle dance. Cuttlefish flash intricate patterns on their skin. Birds perform elaborate sequenced mating displays.
It's a temporal language. The meaning is encoded in the duration, the sequence, and the rhythm of the movement.
Exactly. What if we use a VJP2-style model to observe these animals over massive time frames, millions of hours of footage? It could learn the underlying syntax of their movement, the temporal structure. This wiggle, followed by that turn, always precedes this action.
So you're decoding the grammar of motion. Yes. And then we use a T3 style transfer to map that discovered temporal logic onto the logic of human language. We could potentially translate a bee's waggle dance, not just as a simple statement like food is 500 meters north, but with all the encoded nuance of distance, quality, urgency, and potential danger converted directly into human-readable text.
You're translating the language of time into the language of words.
We could finally start to understand languages that are purely enacted, not spoken or written.
That is a beautiful thought. It frames motion as just another language that an AI can learn to tokenize and parse. It bridges the gap between the physical world of animal behavior and the symbolic world of human language. It suggests that language isn't just spoken, it's performed.
So to wrap this deep dive up, we started with models that see the world as a disjointed stack of photos. We are ending with models that are, for the first time, learning to see the invisible thread that connects those photos: time.
The big takeaway for me is that we are finally addressing the illusion of understanding. We are stopping the models from cheating by looking at static cues. We are forcing them to learn the hard stuff: physics, causality, consequence.
And once they learn that, they stop being just passive observers or creator generators. They become planners. They become agents. They start to step out of the screen and into the physical world.
And that is when things get really, really interesting, when the map the AI creates starts to accurately predict the territory.
So I'll leave you with this final thought. We, as humans, rely on our perception of time to define our reality. Past, present, future. It's how we organize our entire existence. If an AI, using a perfect internal world model like an advanced VJP, can predict the future state of your immediate environment better and faster than you can, who is actually the observer and who is just catching up to a reality that's already been calculated?
That is a haunting thought. We might end up living in the past relative to the machines that are living in our predicted future.
Thanks for listening to Talk Tensors.
See you next time.